Good morning, friends. I, Professor Arvind Medjodhya from Department of Mechanical Engineering. Welcome you all for the subject Design of Machine Elements 1. Today, let us see two problems on eccentricity. So, the members which are subjected to eccentric loading, on such member, what are the stresses acting? So, we will be looking into such problems. So, starting with the first problem on the eccentricity. So here we have a C clamp on which eccentric load is applied. Okay. So let us see the statement of the problem. Determine normal stresses at the extreme fibers on the cross section AA of a C clamp loaded as shown in figure. So this is the statement, and here we have the figure. So this is the cross section AA, and here we have T cross section of the C clamp. So here you can see the C clamp is subjected to a tensile loading. Here you can see load which is acting away from each other, we can see it as a tensile loading. So from this inner fiber, the load is at a distance of 150 mm, and from outer fiber it will be 150 plus this length, that is 40 plus 100. Okay, this is the total length of the load from the outer fiber, and 150 will be from the inner fiber. Okay, so the magnitude of the load is 80 kilonewton, which is given in the question. Okay, 80 kilonewton. So we need to find the normal stresses at the extreme fibers. Extreme fibers means at the inner fiber and at the outer fiber. What are the stresses induced due to this load P? Okay, so this is the given question. So here in this given question, you need to understand that the load P is the eccentric load. Due to this eccentric load, the stresses produced in the body will be of two types. One is direct stress. The first one is the direct stress due to P. So whenever a load is applied, so there will be stresses will be produced, and when it is of the nature tensile, so direct stress will be induced. We know that direct stress is given by load divided by area. So that is how it is calculated. So one kind of stress is direct stress, and due to this distance, okay, again there will be a bending stress. So bending stress due to the moment of the couple P into E. So here P is the load, E is the eccentricity. Because of that, a bending stress will be induced in the member. So consider the cross section AA of the C clamp. So this is the cross section of a C clamp. So here we have a T cross section. You have to open the data handbook and refer table number 3.A. Okay. In that, if you go for type B, okay, there you will get a T section from the table. Okay, so refer table number 1.3A. So these figures you can find in the data handbook. Okay, for this T section, here this width is given as capital B, and the total height is given as a capital H. Okay, this width is given by small a, and this is a small d, the depth, and the remaining this length is given by b by 2, b by 2. Okay. So here again this figure is alternatively can be drawn like this. So this is the width of b. Okay. So from this we can calculate these parameters. Okay. I'll just open the data handbook for you. So this is table number 1.3A. Here you can see the different cross section, and here as I said type D. Okay, so here you can see type, the first column. In this D you will get this T section. Okay, for this T section we will be having equation for the moment of inertia I, and distance to farthest point C, that is the distance of inner fiber and outer fiber from the load, that is given by C1 and C2. Okay, this is the section modulus Z and the radius of gyration, okay, for the section T. So like this, when you will be having different kind of cross section, you have to refer this table and you have to refer this equation with respect to the cross section which is given. Okay, so in this problem we have a T cross section, so we will be referring this set of formula because here we have the T section. So according to that, you will get the formula for calculating the further parameters. So here the figure is given according to the data handbook. So small a is 40 mm, which is given in the figure. So here you can see this is for small a. Okay, so 40 mm. Next, capital B. So this is the capital B. This width is capital B, and according to the figure, capital B is 100 mm. Next, capital H. The total height is 100 plus 40. Here you can see in the figure 100 plus 40. And small b, okay, here you can see small b is equal to a by 2, that is a. So this is capital B. So we can write capital B minus small a. So capital B is 100 mm and small a is 40 mm. So small b will become 60 mm. Next, small d, depth of this, it is given as 40 mm. So small d is 40 mm. So these are the parameters we write from the data handbook. Okay, refer the same symbol which is given in the data handbook. So from the data handbook, for C1, okay, C1 is the distance of inner fiber to the neutral axis. Okay, so in the figure you can see that from this fiber to this, okay, this distance is given as C1. So this line is of the neutral axis. Okay, so this is neutral axis. So when you refer this figure, okay, here the width is at the bottom, but in the given column here it is at the top. So you need to reverse the direction of C1. Okay, so from here to here it is C1. So when you reverse the direction from here to here, it becomes C1. So this is distance of the neutral axis. So this C1 is given by C1 is equal to A1 x square plus b d square divided by 2 into AH plus BD. Okay, which is given in the data handbook. Okay, so here you can see C1 is equal to AH square plus BD square divided by 2 into AH plus BD, whereas C2 is equal to H minus C1. So this is formula given in the data handbook. So substituting the parameters, you will get C1 as 55 mm and C2 is equal to H minus C1. Value of H is 140. You will get C2 as 85 mm. Next we have equation for the moment of inertia for the T section. The moment of inertia is given by symbol I, and this is the formula given in the data handbook. So according to that, substitute the values. Here we know the value of capital B, we know the value of C1, we know the value of C2, we know the value of small a, we know the value of small b, we need to find the value of small h. This small h again is given in the data handbook. Small h is equal to C1 minus b, which is equal to 50. C1 is 55 and small d is 40 mm, so it is 15 mm. So here you can see in the data handbook, small h is equal to C1 minus b. From here we pick with the equation, that is 15 mm. So substituting all these parameters for calculating the moment of inertia, we will get 13.667 into 10 raised to 6 mm raised to 4. Next, the combined stress at the innermost fiber. So when I say combined stress at the innermost fiber, so according to the given problem, this is the innermost fiber. The fiber which is nearest to the load is known as innermost fiber, and the fiber which is away farthest from the load is known as outermost fiber. So first we will find the combined stresses at the innermost fiber. Okay. So just look into the figure. This C clamp is applied to the tensile stress. When it tends to expand like this, the inner fiber will be subjected to tensile load. So this layer will be subjected to tensile stresses. This layer, inner layer, okay, will be subjected to tensile stress, and the outer fiber will be compressed. So we say outer fiber is subjected to compressive stresses. This you need to little bit imagine the things. Okay. So as it expands, as this and this will move away, when it move away, so this layer is subjected to tensile and this layer will be subjected to compressive stresses. So we say inner fiber is subjected to tensile and the outer fiber is subjected to compression. So combined stress at the inner fiber is given by sigma I is equal to direct stress plus bending stress, P by A plus MB by Z. Okay, you can refer either equation 1.4 or equation 1.10 in the data handle. So here the load is given as 80 kilonewton. So 80 into 10 raised to 3 Newton, what we can write. Area of the cross section. Here the cross section is T cross section. Okay, in the T cross section we will be having again two sections. We can divide into two sections. One is 100 into 40. So this length 100 into 40, and one is again this 100 into 40. So these two sections, sum of these two sections will give us the total cross section area of the T section. So it is 100 into 40 plus 40 into 100 will give us area as 8000 mm square. Next we have bending moment. The bending moment is due to the load into the distance. So here 80 into 10 raised to 3 is the load into the distance 205. So how this 205 mm? So we have eccentricity, that is distance of CG from the load, that is 150 plus value of C1, because we are finding the bending stress at the CG. So here we can see, so here we are finding at the CG, innermost fiber. Okay, so 150 plus this distance, that is neutral axis. C1 is the neutral axis. This distance you have to consider. So for calculating the bending moment, you should not consider the distance of the inner fiber. Okay, you should consider the distance of CG from the load. That is called as the eccentricity. Therefore, eccentricity is at a distance of 150 plus 55 mm. So total it is 205 mm. So this is eccentricity. So 80 into 10 raised to 3 into 205 will give us the bending moment 16.4 into 10 raised to 6 Newton millimeter. So this is the bending moment. And so here in this parameter, now we know the value of P, we know the value of A, we know the value of bending moment. We need to find the value of section modulus at the inner fiber. So section modulus is given by I by C1. Since we are calculating for the inner fiber, it is I by C1. If it is for outer fiber, then it is I by C2. Okay, so I by C1. So I value we have calculated already, which is 13.667 into 10 raised to 6 mm raised to 4 divided by C1 is 55. So you will get section modulus for the inner fiber as 248.49 into 10 raised to 3 mm cube. Substituting the parameters in this equation now, we get stresses of the inner fiber, combined stresses of the inner fiber. This is value of P divided by A plus MD divided by Zi, which is equal to 76 Newton per mm square. This is the stresses induced at the inner fiber, that is combined stresses induced at the inner fiber. Next, let us see combined stresses at the outer fiber. So we'll write sigma naught, which indicates combined stress at the outer fiber, direct stress minus bending stress. The difference you can see here, we had written direct stress plus bending stress, but here we are writing it as direct stress minus bending stress. This negative sign indicates, or why we have considered negative sign, because compressive stresses are induced at the outer fiber. Because of that reason we are using negative sign. So P by A minus MD by Z naught. Here the value of P remains same, that is load. Value of area remains same, cross sectional area. The bending moment value remains same because it is with respect to CG, so that is also remains same. Only the section modulus at the outer fiber that changes, I by C2. The value of I is same, C2 is 85. So we get section modulus as 160.79 into 10 raised to 3 mm cube. Substituting these parameters in this equation, we get combined stress at the outer fiber as negative 92.62 Newton per mm square. This negative sign indicates that it is compressive in the nature. Hence, we found the combined stresses at the inner fiber as 76 Newton per mm square, which is tensile in the nature, and at the outer fiber 92.62 Newton per mm square, which is compressive in the nature. So this is the solution for the given problem. So for better understanding the problem, okay, you have to refer the data handbook. Then only it will be easy to understand. And this PDF will also be posted in the group. You can refer this PDF where complete explanation you will get for each step, and refer the data handbook. So next we will move to the next problem on the eccentricity. Okay. So here we have the problem statement. A mild steel bracket shown in the figure, okay, so this is the figure, is subjected to a pull of 10 kilonewton. So this is the pull of 10 kilonewton. The bracket has a rectangular cross section. So this is the cross section we are talking about, which is rectangular in the section, rectangular cross section, whose depth is twice the width. So whose depth is twice the width. That means H is 2 times the B. Okay, that is what they have given. Depth is twice the width. If the allowable stress for the material is 80 Newton per mm square, so that is the allowable stress in the material, 80 Newton per mm square. Determine the cross section of the bracket. So we need to find the cross section of this bracket. So that is nothing but value of B and H we need to find here. So if you look into the given data, the value of load is given as 10 kilonewton, that is 10 into 10 raised to 3 Newton. Allowable stress as 80 Newton per mm square. Height of the cross section is twice the width. This is what they have given. And this load 10 kilonewton is applied at an angle of 60 degree with respect to this vertical. Okay, this is the given problem. So first thing what we need to do here, we have to resolve this force into vertical and horizontal component. This 10 kN we need to resolve into vertical and horizontal component. So resolving into horizontal component, we write Fx is equal to F sin theta, and Fv, when we resolve into vertical, we write Fe is equal to F cos theta. This is known to us. So vertical component, Fe is equal to F cos theta, that is angle theta is 60 degree. We get vertical component as 5000 Newton, and horizontal component as F sin 60, we get 8660.25 Newton. So this is the horizontal component. Next, let us see first considering the vertical component. So this is the vertical component. We will consider this force now. So considering the vertical component, bending moment due to the vertical component. So when the load is applied here on this axis, okay, the stresses induced at the fixed end, okay, the maximum stress will be induced at the fixed end. So due to this vertical load, this maximum stress will be induced, and here on this section there will be bending due to this vertical load. The bending stresses will be induced here because of this distance 150 mm. Okay, so the bending moment will be load into the distance 150 mm. So MBV, that is MB is a bending moment due to the vertical load. So vertical load Fe into 150. 150 is the distance. So vertical load we have 5000 Newton into 150. We get bending moment as 75 into 10 raised to 4 Newton millimeter. And due to this bending moment, the bending stress induced is sigma 1 is equal to MB divided by Z, okay, where Z is section modulus, which is given by I by C. This we have come across in the previous problem, okay. So we need to find moment of inertia and distance of CG. So for a rectangular cross section, okay, here we have this rectangular cross section. For rectangular cross section, moment of inertia I is given by dh cube by 12, or we also write it as dv cube by 12. So here we don't have the values of b and h, okay, but we have the h value in terms of b, that is twice the width, we have the height. So I will write h as 2 times b. So moment of inertia can be written as 2 by 3 into d raised to 4 after resolving this. Next, C, that is distance of neutral axis from the extreme fiber. So here for a rectangular cross section we have C is equal to Ci is equal to C naught, or also we can write C is equal to C1 is equal to C2 is equal to h by 2. And here h value we have in terms of b as 2b. So 2 will get cancelled, we get it as b. So value of C is nothing but b now. Therefore, section modulus Z is equal to this, Z is equal to I by C is equal to, substituting the value of I and C, we get 2 by 3 b cube. Therefore, bending stress induced at the bending stress induced due to the vertical bending moment MBV is given by MB divided by Z, that is nothing but bending moment 75 into 10 raised to 4, and value of Z we have 2 by 3 b cube. So we substitute that value, 3 will go to the numerator here. We get 112.5 into 10 raised to 4 divided by d cube. Okay, write it as equation number 1. Due to this vertical bending moment, tensile stress induced on the upper surface and compressive stress is induced on the bottom surface. So here you can see this, the load is applied here vertically downward. Downward means because of that it will tend to sag, that is sagging. When the sagging moment is there, on the upper layer it will be tensile stresses and at the bottom layer it will be compressive stresses. So that is what here we have given. Due to this vertical bending moment, tensile stress induced on the upper surface and compressive stress induced on the bottom surface. Next, let us consider horizontal component. The horizontal component of the given load is an eccentric load, because here you can see the horizontal component will be acting in this direction, that is horizontally, which is parallel to the neutral axis of this rectangular cross section, and it is at a distance of 200. So this 200 is nothing but the eccentricity what we are talking about. So because of that, the rectangular cross section is subjected to eccentric load. Okay. Due to this load, the steel bracket is again subjected to direct stress and bending stress. Direct stress due to the horizontal component FH, and bending stress is due to the horizontal component into eccentricity. Eccentricity is nothing but this distance 200. Okay. So bending moment is given by FH into E, that is horizontal load into the eccentricity E. We get 1.73 into 10 raised to 6 Newton millimeter as the bending moment. Direct stress due to the horizontal force FH is tensile toward the bending, tensile toward the component. Okay. So when this horizontal force is applied, okay, so this bracket tends to move in this direction horizontally. So that means the entire bracket is subjected to tensile stress, and due to the bending moment, due to this eccentricity 200, it is subjected to bending stress. And the bending stress due to the couple on the upper surface is tensile and bottom surface is compressive. Again, due to this eccentricity, the bracket tends to sag. So it bends in this sagging moment. The upper layer is subjected to tensile stress, lower layer is subjected to compressive stress. So combined stress on the upper surface is given by sigma 2 is equal to direct stress plus bending stress. So here we know the FH value, we know the cross sectional area which is already calculated, 2b square, that is d into h is the cross section of the rectangular cross section, where h is 2 times b, so it is written as 2b square. MVH we have calculated 1.73 into 10 raised to 6. We have to calculate the section modulus Z, and section modulus Z is calculated in the previous calculation as 2 by 3 into d cube. So we will substitute all these parameters here in this equation, that is load, horizontal load divided by area plus horizontal bending moment due to horizontal load divided by section modulus. We can write combined stress on the upper surface sigma 2 is equal to 4330.127 divided by d square. So just cancelling these things, we get these parameters. Now there will be two tensile stresses on the upper surface. One is due to this horizontal load and one due to this vertical load. Okay, due to this vertical load, there is a tensile stress on the upper surface. So this is the value of the tensile stress on the upper surface. This is the value. So adding these two will get a total tensile stress on the upper surface. Total tensile stress on the upper surface sigma is equal to sigma 1 plus sigma 2. Sigma 1 value is this, sigma 2 value is this. Resolving that, and here the value of allowable tensile stress is given in the question as 80 megapascal or 80 Newton per mm square. Substituting this value, resolving the equation. Once you get this equation, you can calculate the value of B in your calculator. Okay, if you have a 991 ms calculator, you can go for equation mode, and here we have a cubic, therefore 3-degree equation, and substituting these values we will get the value of B as 36.46 mm. So approximately we can write the value of width as 36.5 mm, and width of the bracket is considered as 36.5 mm, and depth of the bracket as h is equal to 2 times b. So 2 times of this you will get it as 73 mm. So here we have calculated the value of the cross section, that is b and h. So this is a solution for the given problem, because this is what they had asked in the question. Determine the cross section of the bracket, that is b and h. So we will form the cross section of the bracket b and h. So this is the solution. Okay. Thank you. In the next video we will see 2 more problems. Thank you.